We're going to finish off this section by reviewing some ideas and concepts that we should be very familiar with from traditional vector spaces. The way we are going to handle them with abstract vector spaces is exactly the same. So this should be review more than new information. So we are familiar with the idea of a linear combination. If V is a vector space, if V1, V2, all the way to Vn, if these are vectors in V, then a linear combination of the vectors V1, V2, Vn is going to be a scalar times the first vector plus a scalar times the second vector plus a scalar times the last vector. Okay, scalar times a vector plus a scalar times a vector plus a scalar times a vector and so on. All right, that's a linear combination of vectors. So we've seen this in a traditional vector space, but if we go to a vector space like, let's go to M22, we could look at something like 3 times 1, 1, 2, negative 1 minus 5 times 4, 0, 1, negative 3 plus 2 times 6, 0, 1, 0. Okay, this is a linear combination in M22 of these three 2 by 2 vectors. Okay, these three 2 by 2 matrices, which are vectors in the vector space M22. Okay, similarly, we define span just as we do with a traditional vector space. If V is a vector space, any vector space, traditional or abstract, let V1 to Vp be vectors in the vector space V. The set of all linear combinations of those vectors is called the span of those vectors. Okay, so the span of a set of vectors is the set of all linear combinations of the vectors. So here I have one linear combination of these three vectors. We look at all possible linear combinations of these three vectors by changing the coefficients, by allowing any possible real number coefficients, we would get the span. The span is all the possible linear combinations of a spanning set of vectors. Okay? And as we've previously seen, if we take a set S, subset S of any vector space V, and then look at the span of that subset, that is going to be a subspace of the vector space. Now, I'm not going to prove this because we've actually already proved it. The proof for this is exactly the same as how we did it when we looked at a traditional vector space. And that is the advantage of these vector spaces because they have all the same properties. So the theorem in the abstract case is going to be exactly the same as the proof of the theorem in the traditional case because all the properties of those a vector space are the same. And we're focused on the properties, not how the vectors in the space look. Okay, so a span of a set of vectors is a subspace of a vector space.